Welcome back, everyone. I'm Jordan Giesecke, and this is The Limiting Factor. A few weeks ago, HyperChange published a video titled Transition Metal-Free Cathode Breakthrough with Sean Mehta. I read that research paper and I was fascinated. So, I decided to contact the research team to get some deeper insights into how this battery actually worked. They agreed to an interview, and that's what we'll be discussing today. I'd like to introduce Professor Chongyin Wang, who oversaw the research paper, and Chongyin Yang, who led the research paper for the University of Maryland. Thanks for joining us, Professor Wang and Chongyin.
Yeah, you are welcome.
Thank you.
So we are very excited to have this
Great.
opportunity.
Great. I'm excited as well. When I started reading this research paper, there was a lot of new concepts for me that I had to get my head around. It's almost like alien technology for me. So the first question I have is, you're based at the University of Maryland, and a lot of the media that reported on this mentioned that this was in collaboration with the Army Research Laboratory. What is the relationship between the Army Research Laboratory and the University of Maryland? Do you share a lab, or is it two separate locations, or is there funding involved? How does all that work?
This Army lab and UMD is separate, but we are very close. The reason we have a lot of joint projects. In 2014, University of Maryland and the Army lab established a joint battery center. We call it Center for Research in Extreme Battery. And since then, we joined working on the aqueous battery, we call it water in salt, also working on the non-flammable organic electrolytes. So the water in salt electrolyte actually is different from traditional electrolytes because we put a lot of salt inside of water. So make the aqueous battery stability window larger than before. Before only 1.5 volt to 2 volt. So right now we can go to the 3 volt. If we go to the 3 volt, we have a possibility to build high energy density aqueous battery, because aqueous is really safe. So that's the reason we have a long-term collaboration with Army Lab.
That's interesting, and we'll get into that a bit more deeply, because for the audience, now my understanding, you can correct me if I'm incorrect here, is that generally if you run a current through water, it breaks down at about 1.5 volts into hydrogen and oxygen. And what you're actually able to do is take a water-based electrolyte and boost that voltage window up by quite a bit. So we'll start with the title of the research paper, and then we'll dig into what each one of these words means. So the first thing was that aqueous electrolyte. What are the typical electrolytes that are in a conventional lithium-ion battery, and how does an aqueous electrolyte differ from those? And what are the advantages of an aqueous electrolyte?
So aqueous electrolytes, the advantage is non-flammable, also cheap. But a disadvantage is the stability window is narrow, just say 1.5 volt to 2 volt. But organic electrolytes, they have a wide electrochemical stability window. They can go to the 4 or even beyond 4 volt. So that means use organic electrolytes, we can build high energy cell. But a disadvantage is they are flammable, and so they are not safe. So right now, what we did is we want to use aqueous electrolytes, but extend the stability window so we can get a high energy density and also keep intrinsically safe. So what we did is we put a lot of salt inside water because they have a strong interaction between salt and water, so water will be stabilized. So they will not decompose beyond 2 volt. So we can extend it even after only beyond 3 volt, water can start to decompose. So then we have an opportunity to build high voltage aqueous battery. So that is the motivation for us.
That's excellent, and that covers the the key points I was interested in with regards to an aqueous electrolyte, which you're working on for this paper, and what's called an organic electrolyte for a typical lithium ion cell. Typically, it's a chemical that's used. Let's see here. Is it ethylene carbonate? Is that what's usually used in the electrolyte for a typical lithium ion cell?
Yes.
Is that correct?
Yes.
Okay,
Yeah. Yeah.
And of course, any chemical that you're going to use is going to be more expensive than water. So it's preferable to use water. And then on top of that, water's non-flammable. But water, an aqueous-based electrolyte comes with all these other different challenges, which it looks like you've done a great job of solving in this research paper. So that covers aqueous. The next word people wouldn't be familiar with or might not be familiar with is halide. Typically, batteries are made from, say, a transition metal such as nickel. What is the difference between a transition metal and a halide? Why would you prefer to use a halide versus a transition metal?
Yeah, I can. Yeah. So currently, state-of-the-art lithium cathode, especially cathode, is using the redox reaction of the transition metals to actually store the energy. But the problem is that this transition metal is like very expensive, and also it's the mining it is actually a very unethical process, because it's only like cobalt. You can only mine it in the Africa. So yeah, everybody knows there is some kind of ethical problem with that. So the industry always trying to replace cobalt, and so they are trying to use a high nickel cathode, but it still has a problem, because if you stop using cobalt, the nickel price also will rise, right? So, and in this chemistry, actually we can manage to like replace all the transition metal, and instead we're using the redox reaction of the halogens. It can provide the same or even higher energy density by the redox reaction of the halogens. Another great advantage is just we're using the halogen, which is very abundant elements that will replace the high cost transition metals. So we can largely reduce the cost of the cathode, which also the main cost of the whole lithium batteries. So that's I think that's a really big breakthrough for the whole industry.
Oh yeah, excellent. It's cheaper, higher energy density. And then I was speaking with somebody else, and they suggested that lithium in its natural state is sometimes actually bonded with halogen in the deposits. Is that correct?
Yeah, the lithium chloride and the lithium boride actually is the most common salt we can find in the nature on the earth. Actually, there is a huge amount in the sea. Of course, you have the chloride and bromide salt in the seawater, right? Also, I found out that there like lithium bromide, lithium chloride is also largely distributed in the naturally minerals. So it's very cheap and very abundant. So it's and the rest part is only graphite, right? So you can even find the natural graphite in the minerals, and which is quite cheap. So the whole material level is just a natural materials. It won't have the high cost for that.
I didn't even realize that about seawater. That's really exciting. It's got the wheels turning in my mind, because generally, in order to make the cathode for a battery, you have to mine all these transition metals, which is of course toxic, as you said.
Yeah.
And then you have to extract the lithium separately and separate it out, so it's just lithium hydroxide or lithium carbonate. And then you bake those two things together to create the cathode. But what you're saying is, and correct me if I'm incorrect here, we could potentially just take seawater and separate those chemicals out of seawater, and then we could directly use those to create a cathode material.
Yeah, actually, we did that every day, right? We eat sea salt every day. So we just simply separate the water from this salt. So we only need to purify the salt we need, like lithium salt, from this kind of sea salt. And it's just a very simple chemistry, just not a very complex thermal process like we use for the lithium cobalt oxide or nickel oxide.
Finally, the last words in the title are conversion, intercalation, chemistry, and graphite. Now, correct me if I'm wrong, but my reading of that is that the anode in this is the same graphite anode in a conventional lithium-ion battery. That is, lithium ions are stored in the anode. I'm assuming that the conversion refers to the cathode side. Can you explain the difference, how this differs, a conversion cathode from the typical intercalation cathode in a conventional lithium-ion battery?
So we need some background for this cathode. So actually, right now, the state-of-art lithium battery, we're using intercalation chemistry like lithium cobalt oxide, or lithium or high nickel NCA or something. So we're basically using the layered material, which is normally the transition metal oxides layer, right? So we insert or extract the lithium ion into or outside of this kind of layer chemistry. So we call it intercalation type. The conventional type, actually, we break all the chemical bond between the lithium ion and another anion type host. So during the whole reaction, which means the whole material, the cathode material will convert into another type of material during the charge and discharge. The advantage of these chemistries are they normally provide a very huge capacity, because you do not need to maintain a very heavy host when you extract the lithium ions. The advantage is normally this kind of chemistry don't have a very high reversibility. So for example, the typical example for the conversion type is lithium sulfur cathode, and also the some kind of transition metal fluoride, transition metal chloride, this kind of cathode we call the conversion chemistry. But actually, in our work, we actually combine the advantage from both the conversion type and the intercalation type. We use the conversion reaction of the bromine and the chloride to provide a huge amount of capacity at the high redox reaction potential, right? So that's why we can provide a high energy density. Instead of just simply convert to another reaction products, we actually store these reaction products by intercalate into the graphite interlayers. So that's guarantee a very high reversibility. So we basically combine both advantage from these both types. So that's why this chemistry is so extractive. Yeah.
I'll paraphrase this and see if I understand it correctly, because there's some new concepts in there for me. Typically, a conventional lithium-ion battery has a layered structure and the lithium ions are stored in between it. With a conversion chemistry, there's a reaction that takes place, and there's no host structure required to store those ions. So because there's no host structure, there's less dead weight. However, those reactions, once they take place, there's unwanted chemical reactions that occur and then are free to roam around the battery. Whereas what you're saying is the reaction occurs with that conversion, but you've also put some graphite into the cathode, which kind of soaks up those unwanted reactions. Is that right?
Yes, that's right.
Yes.
So we use the graphite interlayer to protect the highly reactive reaction products that prevent the side reactions. So to provide a very high reversibility. When you want to discharge it, it will release from the graphite and combine with the lithium ion, which migrate from the anode and combine together form a lithium bromide, lithium chloride salt again. So it will guarantee a very high reversibility for the next cycle.
That's brilliant. And my next question is, how did you even come up with this? Because did you use artificial intelligence? Did you see research from other people that sparked a bright idea in somebody? What was your inspiration? Because it just seems like there's so many different new pieces that are combined in this battery. I wonder what the genesis was.
So I think we can say this, we have a motivation to develop a high energy, cheap, high reversible new cathode. That is our motivation. Second, we have the right person, no different technology. Chongyin is really good in the water in salt electrolytes. Also, his background is physics. So he knows a lot of physics, the reaction and electrochemistry. And Ji Chen, another postdoc, is really good on the graphite. And also the like bromine chloride integration is expert on that one. We just have a good motivation, good person, good time, put everything together. And then we get this good idea. In this work, Army Research Lab did a lot of simulation work and to help us to understand the new chemistry, how the bromine chloride intercalculate into the graphite. Also, Organic Lab did a lot of in situ characterization to confirm the simulated result, also provide additional information on the bromide chloride valence change during the electrochemical process.
That's a brilliant summary. Thank you. And it's also a good time to start getting into sort of the specs, the type of information that the general public is interested in, such as what energy densities were achieved compared to a conventional lithium-ion battery. And yeah, so we'll start with that, energy density, and then we can also get into things such as cycle life.
So actually, this is from our paper. This graph tells us theoretically how much energy density we can deliver for our technology here, which is a lithium bromide chloride graphite cathode, compares to these blue bars are all for the state-of-art lithium cathode, where intercalculation type, the LFP is a lithium iron phosphate. The big companies like Tesla or other EV companies are trying to use the NCA or NCM. So compared to this intercalculation type, our cathode, the energy density can be even much higher than this force, right? So the future is here, at least for some academic groups, saying that we're probably using the convention type like lithium sulfur or even lithium air, but compared to lithium sulfur, based on the weight, the energy density is a little bit lower, but actually, so this is a volumetric energy density. So actually, the lithium sulfur use a lot of low density carbon host, right? Normally. So if we compare the volumetric energy density, this technology is even higher than lithium sulfur. So cathode can at least reach the same level or even higher level than all the state-of-art lithium cathode. These lines represent the different energy density level. So our technology, which couples with a graphite anode, is here. It's a highest energy level for any kind of lithium chemistry we ever built. These blue points are the state-of-art practical fuel cells, which is the NCA coupled with graphite, NCM 622 with graphite, the lithium cobalt oxide with graphite, and the lithium iron phosphate with graphite. And we also compared with all the mature aqueous technologies. So they are way down here, right? So it's also provides the same safety and the much higher energy density compared to the other aqueous technology.
Excellent. That gives me I didn't fully appreciate how much better the volumetric energy density was. I had noticed the gravimetric energy density.
Mm-hmm.
How was the cycle life data that because I think I saw some cycle life data just above there. So how did that compare with other chemistries?
Right now, it's the cycle life is not as good as the most state of art. So we trying to we successfully run this battery for like around stably for at least 200 cycles, but still the decay is per each cycle is still higher than the state-of-art chemistry. But we are just beginning. Maybe hopefully in the future we can reach the same reversibility as a state-of-art cathode, but deliver a much higher energy density and a much higher safety in the future.
Absolutely. This is excellent results for the first try for a new chemistry. And generally it takes, 5, 10, 15, 30, 40 years to develop a chemistry sometimes. So considering this is the first go, that's excellent. And we'll get into the roadmap here in a second as to how you plan on approaching it and tackling it. So for the battery that was used in this paper, at a cell level, what type of energy density would that have equated to?
So at the cell level, we can actually reach, I think, at least 300 to 400 watt-hour per kilogram. That depends on, because we actually, this is still a theoretical. If we gonna commercialize that, we definitely have using a different cell type, structure, or maybe some kind, we need using other current collector or something. So we cannot give a exactly number for right now, but my assumption is at least we can reach 300 or maybe 400 in the future for the cell level.
So right now we still use water in salt electrolytes in the paper. For the water in salt, it's hard to use the graphite. So we try to use graphite, but the cycle life is still not as great as the organic electrolytes. So right now we try to use organic electrolyte to replace the water in salt.
All right, that gets into the sort of the roadmap. So where you are, what you've done so far is just kind of this battery cell that you've created with this research paper is kind of a proof of concept, and you were doing a lot of just basic information gathering, and you weren't necessarily trying to push this cell to its limits. You were just trying to see if it worked. So now, what does the roadmap look like going forward? It sounds like the next thing you're going to do is replace the aqueous or water electrolyte with sort of a conventional electrolyte and see how it performs then.
Yes. So that step we can easily apply our cathode in the existing production line. So we just use this cathode into the existing little battery, replace the cathode, and use the different organic electrolytes. Then we can make it cheaper and also high energy density. So that is the goal. Separately, another way is we're still working on the aqueous electrolytes, make the graphite stable in the aqueous electrolytes. So that is a challenge. Because that is really beyond the thermodynamic stability window.
And now we're getting down to the final few questions here. In terms of the broader spider chart for this chemistry, where is it strong and where do you see it as being weak, or is it still early days? Because my perspective listening to everything that you've said so far is this has the potential to match or beat conventional lithium-ion batteries in terms of energy density. We don't know in terms of cycle life yet because you still need to do some experimentation there, but it has the potential to be much cheaper than a conventional lithium-ion battery. Is there anything I'm missing there?
So yeah, we in terms of energy density, rate capability, the cycle life, the cost, and the safety, we also compared with the star materials like high nickel cathodes and the lithium iron phosphate, like Tesla recently trying to use in the EVs. So in terms of energy density, we mentioned about like we can provide even higher energy density compared to the high nickel cathodes or the iron phosphate. And the rate capability, at least we can reach the same level with high nickel ones. And this phosphate naturally have the better rate capability, but it provides a lower energy density. So power density wise, it's basically the same. So for the cycle life, it's our weak point now. We can only reach maybe 200 cycles for now, but I don't believe it's a big problem in the future, because after we get to the full understanding of the whole chemistry, we can simply just modify, find what is where is a weak point, and we can modify it and reach a high cyclability. Because in theory, it should be provided a very perfect reversibility. So we don't worry about in the future. And the most attracting thing is the low cost. And not only the material wise, not only the raw material is cheap, also maybe I think we will mention that later, that the processing of the whole cathode material is cheaper. And for the safety, also the Aqueous system can provide a very high safety for the whole battery instead of the organic solvents. So that's pretty much everything for spider chart for the whole comparison.
That's beautiful. That's you can frame that. that's really impressive.
Okay.
Thanks for pulling that together.
Okay.
The only question I have left would be, for a chemistry like this, how long does it usually take to go from lab to market? I know it's the type of question where it's how long is a piece of string and there's no way to really tell, but it seems like this is, like you said, I was reading through the research paper and it seemed like it was really easy to manufacture and produce and adapt to existing manufacturing lines. So what do you envision as the future for this chemistry? How do you see it playing out in the next 5 or 10 years?
So if we really want to apply it into the real battery, the shortest way is transfer to the organic. If we can successfully transfer from aqueous battery to organic, and then we can easily move to the industry, let the industry just try and build a commercial battery. Second is, if organic part we have a breakthrough and can successfully make the graphite stable, then we can also go to the industry to try. So right now we're still in the lab scale, but I closely work with the SAFT. SAFT American is closer to the UMD. And so we have a long-term collaboration. And for the RPI project, actually it's the SAFT, UMD, and Army Research Lab. So 3 of us right now, we work together to build the commercial aqueous battery. So RPI really want to use lithium manganese oxide and lithium titanium oxide, both as anode cathode, and build a real water-in-salt electrolyte. So in the early stage, we also have a small business company involved. The small business is a lithium oxide, Leox, and they are in California, and they are really good on the lithium oxygen cell, also in the good in the electrolytes. So we have a long-term academic, national lab, industry collaboration. So I think because we have a team, long-term team, if the technology in the lab is ready, we can easily transfer to the industry and they can try. So we have the internal mechanism and transfer from academic to the industry. And SAFT is a really good world leader lithium battery company. Yeah.
Excellent. It's good to hear that you're working with industry on these things and it's actually being carried forward in some way. And what I'll do is, after the interview, I'll get some of the links to the organizations that you just mentioned and link them in so people can take a look and learn about the organizations that you mentioned. And to cap things off, the research paper that you're working on with or the research that you're working on with the organic electrolyte, when can people expect to see more research coming out on this? Do you have another research paper planned?
Yeah, recently we have another postdoc. He really make a really good progress. And I think within maybe 1 year, we can publish another paper. And we hope based on that result, we can talk to the industry and see is they possibility to transfer this technology to the industry and validate and build a large dipole cell.
With that, I think we can wrap things up. Thanks for your time, Chun Sheng and Chongyin.
Thank you.